This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
A ring of superheated plasma, reaching tens of millions of degrees, is inherently chaotic. The closer engineers get to sustaining these reactions, the more violently the plasma twists and ripples before collapsing against its containment walls. For decades, the industry has answered this instability with sheer size. Under the logic of monolithic scaling, engineers try to contain the chaos by building a larger, more powerful singular magnetic field to crush it. This reliance on a single, continuous field creates machines of staggering physical complication. To wrap an entire core in a monolithic architecture, designers must route thousands of dense, overlapping cables just to maintain the baseline magnetic pressure. In a system built this way, every single component is tethered to the same global state. There is no isolation between failure points. Because the containment relies on one unified field, a microscopic thermofluctuation in a single millimeter of plasma can trigger an unchecked cascade, shutting down a multi-billion-dollar reactor in milliseconds. Early computing faced a similar ceiling. Mainframes were impressive, bespoke monoliths, but if a central processor failed, the entire machine went dark. Computing only reached global scale when it adopted the server farm model, networking thousands of independent, standardized units to generate massive collective power. To become a viable global infrastructure, fusion must follow that path. It requires moving away from brute force scale and toward precision modularity. This is the baseline unit for that modular architecture, the Omega-1 pilot cell. This isn't a colossal, bespoke facility. It is a compact, highly controlled stainless steel vacuum chamber designed to master the physics in an isolated environment. Inside this cell, the containment strategy changes. A discrete flux lattice, a web of independent superconducting loops, replaces the single massive global field. This diagram illustrates how the lattice operates. While the main magnetic ring provides the base, these smaller, independent, discrete loops are superposed along the outer edge. They structure the boundary layer of the plasma directly. When a pocket of turbulence spikes outward, a local loop independently increases its intensity to push back, smoothing out the defect without altering the rest of the containment field. Stability comes from enforcing a rigid topological structure at the edge, rather than relying on the brute force magnitude of a monolithic field. But a physical lattice is only half the solution. A millimeter of plasma can deform and collapse in millionths of a second. To manage that speed, the hardware is driven by the TFLF control kernel. It operates on a sub-microsecond loop, executing deterministic commands faster than the plasma can warp. We can track that speed in this signal flow graph. Magnetic data travels directly from the sensors into a model predictive control block, which calculates the exact counterforce needed and fires a command straight to the lattice actuators. Before any command reaches the hardware, it must pass through a hard-coded safety filter. If the math generates an unstable or rogue instruction, the filter physically blocks it from actuating. By bounding the actuation with strict software invariance, the thermodynamic chaos of a fusion reaction becomes a manageable high-speed control problem. Mastering a single cell is the prerequisite. The advantage is realized when that cell multiplies into a matrix, forming the Omega-2 multicell cluster. These cells are linked by a shared power and control bus, but their failure points remain physically and magnetically isolated from one another. Look at node 7 in this 12-cell cluster diagram. If it flashes red with a severe instability, it immediately disconnects from the central power line and powers down. The remaining 11 nodes instantly reroute the power flow to compensate. This matrix approach turns fusion from a fragile science experiment into a resilient industrial power plant. Managing a matrix of this complexity generates a byproduct that is almost as valuable as the electricity, a continuous stream of pure telemetry. Every sub-microsecond correction feeds into FluxOS, creating a digital public infrastructure for fusion. It provides a standardized software layer for testing, tracking, and simulating digital twins across the entire industry. With the hardware modularized and the data standardized, deployment becomes sovereign. Nations can purchase and scale fusion infrastructure node by node to meet their exact grid demands. The era of relying on singular, colossal machines is reaching its physical limits. Architecting the infrastructure to scale, control, and deploy fusion repeatedly is the final milestone in the global energy race.